Welcome to today's daily challenge. Let's begin our question of the day. Question 958, check completeness of a binary tree. Okay, given the root of a binary tree, determine if it is a complete binary tree. In a complete binary tree, every level, except for possibly the last, is completely filled, and all nodes in the last level are far left as possible. It can have between 1 and 2 to the h nodes inclusive at the last level. Okay, explanation is pretty clear. So all levels besides the lowest one are complete, which means that depending on the level that you are, for example, the 0th level would have 2 to the 0th amount of nodes. The first level would have 2 to the 1 nodes, except for the last level, which can have, in this case, max 2 to the second amount of nodes, which would be 4, or it can have 1. However, the way that this would be an incomplete tree is if the nodes were not all to the left. I don't know how to what is the property here that nodes. Well, first of all, I would say that you would have to start distinguishing. You would have to include the terminology left and right, because, for example, this node has a left node and a right node. I guess what the statement is here is that you can the last level cannot have a right node without possibly having a left node, or without having a left node. So this right node could not exist without having a left node. So there would be no skipping. And additionally, if this wasn't here, if it was just 1, 2, 4, and 3, 6, this would also not be correct, because this 6 would ideally just be, well, for it to be complete, it would have to be to where this 5 is. Let's look at the example. Every level. So yes, this is a complete tree. In example 2, this is not a complete tree. And I'm just also wondering if this is a dead giveaway to how to solve this problem. You would see here a breadth first search traversal, where we go 1, 2, 3, 4, 5, null 6. I'm wondering if we could just basically iteratively go through this in the breadth first format, and then see if there's any numbers, if there's any nulls preceding a number. And in that case, we would return null, that it's false. Otherwise, if it's a contiguous sequence of numbers and then at some point nulls start to appear, that's perfectly fine. That is definitely one way of thinking about it. I am also thinking of maybe a quicker solution where we don't have to populate an intermediate data structure, and I'm wondering if that's actually the right way to do this. Something like, for example, a deep first search, where we could start. We would also start with the leftmost search, diving deep all the way down to this 4, and then maybe we could set some variable, maybe something like max depth, and then as we are continuing to do our DFS, we could kind of see if the condition of that max depth ever gets broken. Yeah, I think that would be quicker, especially that this can be done recursively. Breadth first search is pretty much always done iteratively using a queue. Whereas a DFS could be done recursively. I'm gonna try doing that. Let's make a variable holding the max depth as -1. So as we do that, let's have our general function. So we have the node and then the depth, because each dive into each depth dive is essentially going to increase its depth by 1. And then we can have some conditions here. For example, that if we have reached the last node, then set max depth for sure. So we would definitely want to keep track of that. And then let's see, there's going to be another condition where we could potentially have a little bit of a dive, so decrease the max depth by 1. But once that has been decreased, there's no instance where it could be increased back again. So actually, let's have decreased equals to false. So if we have reached a leaf node, then we want to set max depth, and additionally we would so how about this? If first time reaching a leaf, which we can find out because we have -1, set max depth. If not, if this is a subsequent call, else we could also have something like if depth is equal to max depth, then skip, but else, or no, sorry, we would also have to have an if depth equals max depth -1, then we set decrement to true. So we have true, and set max depth to min, or just set it to depth, I guess. Max depth to max depth -1. Okay. And then just return the DFS of node left and depth +1, and DFS node right depth +1. Okay, so the idea here is that our DFS is going to return true only in the case that the tree that we have just searched is complete. That means that we have a recursive definition for what a complete tree is. Let's actually complete DFS just to complete DFS. Okay. What does this mean again? If the left is complete and the right is complete, then we are complete. And so yeah, I'm pretty sure that we can start coding this. Let's see how we would do this. If we have reached the leaf node. So what does this mean to reach a leaf node? If node left and node right, if not node left and not node right, we have reached the leaf node. Let us now do this. If first time reaching the node, so if max depth equals -1, then set max depth to depth. max depth equals depth. Pretty simple. We are not going to hit this condition ever again because we have just set the max depth. Now, if depth, okay, else, if we are now in one of our consecutive runs and we have again encountered this, well, actually, I would have to return true here. I encountered another depth of the same depth. Nothing, right? I return true. However, right? Am I right here? That if we reached depth, max depth, return true. Else, I guess if depth is equal to depth minus 1, then we set decrement to be true. Oh, so there's another thing here. We have to keep track that decrement has not been set yet, because this is our step down. This is us lowering one more level. And if we are lowering multiple times, then this would essentially be an example of like, this is missing, and then this is also missing. So we would, does it make sense? We cannot have two, we can only have one incomplete level at a time. If we are incompleting the max, if we're decrementing the max depth by more than 1, then we already cannot have that be a thing. So yes, that makes sense. And if depth equals max depth negative minus 1 and this, otherwise return false. Otherwise return false. Okay, so yeah, sorry. As usual, return complete DFS. Did I spell that right? Complete DFS of root node and 0. And one more thing that I always forget to do, depth and decrement. So because this is an nested function, the scope of the variables that are inside it are going to be renewed, meaning that max depth and decrement aren't actually in the scope unless you explicitly non-localize them. And let's see. Okay, so no type object has no attribute left. Okay, so I'm hitting here a condition where I'm calling this or this on a node left that doesn't actually exist. So what do I do if I'm here, for example? Oh, if I am jumping to one of these scenarios, if I have if not node, return true. So basically, if I'm hitting one of these scenarios, then I should be returning true, right? I'm gonna call it my phantom node. Okay, I'm thinking of another quick solution. So what's happening here is my phantom nodes, which are actually just nodes here on the bottom that aren't even displayed here, the null nodes essentially. How about I start treating them as my sort of like bottom layer max depth, right? So I'm not no longer thinking about my leaf nodes. I'm saying that if not node. And if not node, then this is like pretend that this 4, this 5, this 6, and this 3 have sort of phantom nodes. They're ghost nodes that would be there if they were. So for example, there's a left one, there's a right one. For 4, there's a left one, right one for 5. There's a left one, right one for 6, and there's only a right one for 3. Now those phantom nodes are still hold up to the condition that their level cannot increase. It can only decrease by 1, and once it decreased by 1, it no longer can increase, right? So how about I just apply the same logic here? No longer am I looking at the leaf node, I'm looking at the phantom node. And this also does not work. Let's quickly think why. If not node, so this is me leaving my last node. If I'm maxed, if my max depth equals -1, if I have, if this is my first time reaching a node, and well, actually, my first time interacting a non-node would be my left of my leftmost node. So if I was to set that to, so this is by default going to be hit first. I'm going to set max depth to depth. I'm pretty sure that's correct. Spelled everything here right. I'm going to set it to depth, and then continue, and then basically return true. Else, in the condition that, in the case that I am not hitting one of my initial phantom nodes, I'm hitting maybe the right one of this one, I will be using this else statement, and I'm saying if depth is equal to max depth, if depth, oh wait, return true. Maybe that will work. Okay. I think I got it now. I had all the logic right. I was just missing a final return statement here. Here's it one more time. Start thinking of the phantom nodes. The first phantom node is going to set a max depth to the current depth that we have, depth being the level that we're on, and it's going to return true automatically. This is the first time, so it doesn't matter. All subsequent times, we are hitting one of 3 conditions. Either the depth is the same as what we are right now of the right phantom node. If that is the case, then return true. If that is not the case, then the other 2 conditions are either the depth is 1 less than the one that we're looking at, which is fine for us, it's not a big deal. We just set decrement to being true, which means that we've already decremented our max depth. Update the max depth to 1 less than the current, and return true. We're still good. The third and final condition where this would not be actually fine, let me just make this more clear, is the else. The else means that either it is higher, either the max depth that we've just encountered is higher, or it is lower, but lower at a time where decrement has already been decremented once. In that case, we also return false. And I'm pretty sure that that should work. And we are slow. Is this one of those conditions where if you rerun it, yeah. Okay, so this is one of those instances where rerunning it actually makes it run faster. So at 91 is perfect, and beats all the time. All this means is that the time difference is insignificant. 31 and 24, they are insignificant. So yeah, I would say here is the solution. Yeah, feel free to use. Thanks for watching and see you next time.